Ladies and gentlemen, welcome on the first day of the Code Dive conference, on the first session, and of course on the first part of Viktor Kirilov's presentation. At the beginning, some words about our speaker. With 4 years of professional experience with C++ in the games and VFX industries, Viktor currently spends his time writing open source software since January the 1st, 2016, and occasionally doing some contract work. He's the author of DocTest, the fastest feature-rich C++ 98, C++ 11, single header testing framework. His interests are the making of games and game engines, high-performance code, data-oriented design, cryptocurrencies, optimizing workflows, and incorporating good practices in the software development process, such as testing and the use of modern tools like static analysis or instrumentation. Viktor is from Sofia, Bulgaria, and his profession is his hobby. That's about his official bio, but maybe you don't know that as in the spirit of last year, when it turned out that Viktor developed a testing framework having 0 experience with testing in his life, he is now working on a REPL support interactive compilation for the compiler of the name programming language written in itself without even knowing the language, YOLO. So everybody round the applause for the speaker.
So, good morning, everybody. It's a very big pleasure for me to be opening, and also, as a speaker, I'd like to share with you one thing. Each time I give a talk at the conference, it's like divided in 2 parts, the conference itself, before and after. So this time I'll be, for the first time, able to actually enjoy the conference almost entirely, because I'll be over with this pretty soon. So, about me, we covered a bit of this just now. And there's one thing I'm very passionate about, and that's not wasting any time. So, what is C++ known for? Well, performance, expressiveness, it's a multi-paradigm, but it's also a bit complex sometimes, maybe not just a bit. The metaprogramming can get pretty hairy, and it can be even more powerful than it actually is. There's no standard build system and package management, and it takes a long time to compile projects. So, has anyone ever seen this meme before? It's present in absolutely every one of my talks I've given so far, and I don't think that will change. So, this presentation, you can find the slides online even right now on this URL. And I'll start with the what and the why, and after that, I'll continue with the how. I'll cover all these techniques of how to make your builds faster. So, the reality is that some projects in C++ take hours to compile, and WebKit is one such example. Sometimes for a slower computer, it might take even an entire day. And when compilation is slow, both minimal and full rebuild suffer. So even when you have to do a little change and just do a minimal rebuild, we still have to sometimes wait a lot of time, maybe for linking or whatever. And also, all projects start out small, but many of them inevitably grow out to be big, and this always becomes a problem for C++ projects. So here's an example, a case study of the build times for Opera 32, the web browser. So in less than 4 years, they went from 15 minutes of compile time to more than 60 minutes. And even at some point, they incorporated the precompiled header. As you can see, there's a dip in the middle. But even that couldn't offset the big problem they actually faced. So this is a problem which is unique to C++. Other languages don't have this. Other programmers from other languages, they just don't get it. How can a project compile for hours? It's just not in their world. So why do we want to reduce build times? Well, first of all, time is money. If you're getting a big annual salary of $80,000, and if you waste 1 hour each day for building your code and just waiting for builds, that's 12% of your time. And that's $10,000 per developer annually for the company. But actually, each developer brings a lot more value to the company than the salary he receives. So let's just multiply that by 3. And when the corporation is big, like 100 developers, 1,000, it easily goes into the millions. And there's one other thing. So each time you have to build and to wait, you actually are discouraged to refactor and to experiment. And that's unquantifiable easily in money. I mean, you cannot quantify it easily in money. But it's a big problem. Many times the user wouldn't try something out just because he'd have to wait a lot of time. And also, each time we do a mental context switch because we're building and let's open Facebook or something like that, that also has consequences for our attention. So the only logical conclusion we can arrive to is that any time spent reducing build times is worthwhile, especially when the scale is big. How is C++ compiled? Built. So first there's the preprocessor. It takes source files and turns them into a translation units. That means that all the includes are included, all the macros are expanded, and a bunch of conditional compilation also happens with if-defs. After that, the compiler takes the translation unit and it compiles it to an object file. That's comprised of parsing, tokenization, abstract syntax tree building, maybe optimizations, and at the end, code generation. After that comes the linker. It takes all the object files in the libraries and it stitches them together into an executable or into a DLL library. So why is C++ so slow to compile? Well, in order to be adopted in the first place, it had to build up on C. And it had to be interoperable with C. So it inherited the textual include approach of header files. And that led to adoption. C++ exists because it's backwards compatible with C. But includes were initially designed for just sharing declarations and structures between translation units, and not for building high-level, zero-cost abstractions of templates inside of them. Also, the language itself is pretty complex, and there are multiple phases of translation. I think there are 9. And they cannot be parallelized. The language is not context-independent, and each new standard brings more and more complexity to the compilers. And yeah, all of our zero-cost abstractions, they're zero-cost in terms of runtime, maybe if the optimizer does a good job, but our compile times suffer a lot because of them. And sometimes even the preprocessor can become a bottleneck in some weird software. Also, many projects don't have optimally set up build system setups and tools. And sometimes the project is structured badly in the first place. The whole architecture is wrong. And you touch something, you have to rebuild everything, or at least relink a lot of things. So, first of all, the difference between C and C++. If we grab a C code base and we just compile it with a C and a C++ compiler, we instantly get around 12% of performance hit in terms of compile times. But that's not too bad. If we grab a normal C++ 98 code base and we switch the standards with the same compiler from 98 to 11 and to 17, we can go up to 30% or maybe even more or less, depending on the code, of compile time overhead, just because we've enabled a newer standard, even though the code base doesn't use anything new. And this has been measured with GCC 7 on Windows. And the curious thing is, which actually makes sense, is that the language and the standard, they don't affect the optimizer. So when we turn on the optimizations, the difference stays the same in terms of seconds. So this affects only the front end of the compiler, which is actually the parser, because that's where the complexity of the language actually resides. And the newer standards which are upcoming, well, they'll have a lot more complexity to them, like more const expert, more meta classes, not more, but meta classes, concepts, and compilers will have to implement that. Oh, that meme again. So, why do includes suck? Well, first of all, they're textual, they're not symbolic. We cannot cache the results of a parsed header easily, because if it's included somewhere with some macro defined above it, before it's included, then the header can mean something entirely different. So each time we include the header, we have to reparse it and compile it again and again and again. Also, Many times one header depends on another header, even if in theory it shouldn't. And so many dependencies are leaked. For example, if we have a type and it's using as a private field some other type, all we need is the size of the other type in theory, but actually the language forces us to have the definition of that other type as well. So we need to pull in that header for the other type too. And also the same code gets compiled many times. Suppose you have a header which is included in 100 source files, like subvector. Well, you're compiling the same template again and again and again and again. And in this textual include approach, we can end up in the following scenario. So we have m headers and n source files. So the worst cost, the worst case of build cost is m times n. And templates. So for example, stud vector, if we instantiate it for an integer in 100 different translation units, we're instantiating a template 100 times, even though it's the same. And also templates, they force more code to be in headers in the first place. And each time we define a function inside of a header, it has to be inline. So it's either a template, or it's written inside of the body of a class, or it's just explicitly marked as inline. And that means that that function will have to be, again, compiled for each translation unit that includes that header. And also the linker will have to remove all the weak references except for one of them when he's linking the final binary. So that's more work for them. So when we include each of these standard headers in a single source file, we just include that header and we just run it through the preprocessor. And we don't have any code written by us inside of it. We end up with the following numbers. Sometimes it's more than a megabyte of source code after the preprocessor runs. So that's a megabyte of source code that the compiler will have to compile. And it can easily go above 100,000 lines of code. That's without comments. What about boost? Well, for example, boost geometry, if we include it, we get almost 10 megabytes of source code just by including that header. And 500,000 lines of code with Visual Studio. And here, the idea is not to discredit Boost. It's actually an amazing set of libraries. And this is a C++ issue. So C++ doesn't give us a proper way to modularize our code and to build such abstractions. So what are our solutions? First of all, any great talk starts with a big list of disclaimers, right? No. So I haven't tested absolutely every tool and technique here I'll be presenting. And sometimes I link to other resources which go more in-depth into the different topics because we have a lot of topics to cover. And there aren't many exact measurements for the different techniques, but I can tell you which ones are easy to integrate and have a big impact and which ones don't have such a big impact. So the first and the most obvious thing is that when you're developing software, you should be building in Debug because it's much faster. Compilers don't run the optimizer in Debug, and it can be many times faster to just build in Debug. And also there are different levels depending on what you actually need. For example, some game studios, they can't afford to always build in Debug because it's too slow. I mean, 1 frame per second is not debuggable. So they enable some inlining or some intermediate level of optimizations. They do a compromise. So next, the C++ philosophy is that we shouldn't pay for what we're not using, and that includes dead code, unreachable, functions which are never called. And there are a bunch of tools we can actually use to diagnose this. Each of these gives us something like a report in a different way. And some of them are static analysis tools, some are linker tools. You can try a few of them and see what happens on your code base. And in the meantime, you might uncover even some bugs and improve your runtime if you strip down code you don't actually need. Other easy to fix things are if you have unused sources or libraries. After you've removed that code like functions, then you should entirely remove source files which are actually never used or static libraries which are compiled for some reason. For example, they're left in some makefile from years ago and they're no longer needed. And also we should make sure that we compile each source file just once. It's easy to say, but actually many companies are guilty of this. It's easy to just grab a source file and compile it for the nth time instead of factoring it out inside of a static library and reusing it. And so let's go to header files. We should be striving for loose coupling. We shouldn't be using an include everything approach, because then when we touch any header which is included in the everything header, everything gets rebuilt. We should strive to include only the minimum amount of headers which are actually necessary. And again, there are a bunch of tools we can use to diagnose which headers are actually not needed in the different places. The most famous one is include what you use. It's based on Clang, and it's also easily set up through CMake. Next, declarations and definitions. Well, each time somebody asks how to make my builds faster, somebody tells him you should forward declare more things and not define them, and limit your use of header files. So that's true. In this case, we have a forward declaration of a foo function, but the bar function inside of this header is marked as inline, so it can compile and link successfully. But that means that that body of the function will be compiled each and every time the header is included. Also, implicitly inline functions, such as the method inside of the type, they also have to be compiled again and again and again. And templates are also implicitly inline. We should strive to move them out of header files in the first place. We should leave only the forward declarations there, at least when it's possible. And if we're worried about optimizations and inlining, we can use link time optimizations or unity builds, which we'll cover later. Okay. So here in this header, what we see is that we have forward declare foo. It's a structure, but we've included bar. And why is that? Below it, we're defining a type, and there we're using foo as a pointer for the foo pointer variable. And that's perfectly okay. We can go by with just a single forward declaration of foo. But above it, we're using foo by value for a forward declaration of a function, in this case a method. And it's relatively unknown that you can actually go by, even in this case, with a simple forward declaration. Even though the type is not used as a reference or a pointer, but instead of a function declaration by value, we still can go by with just a single forward declaration. But for the bar member inside of the type we're defining, we actually need the entire definition of the bar type, because in order to get to know the layout of the in memory of the type we're defining, we need to know the layout of the memory in the memory of the bar type. So when we're implementing the method of this type in a separate source file, we actually need the implementation of the full type, because there we're not just forward declaring the method, but we're actually defining it. So a definition of types is necessary only when they're used by value, but not inside of forward declarations. And forward declarations are enough if the type is used as a pointer or a reference, because a reference is actually a pointer underneath it, and the compiler knows that the pointer is always the same amount of bytes. Okay, so third-party libraries. It's a good idea to sometimes wrap headers from third parties in wrapper headers, so we don't expose everything from the original header. So we don't include windows.h in our windows wrapper.h, but we just forward declare only the minimum amount of things we would need. And some libraries are good when they actually supply such forward declaration headers by themselves, so the users don't have to write them each and every time. And for example, the iOS forward declaration header for the streams in the STL is such an example. It brings in the declarations for all the streams. Next, we'll talk about PIMPL, which is pointer to implementation or private implementation, or also known as a compilation firewall. And the idea is that we have a wrapper type, which has the interface of our type we want to define, which holds only a pointer to the actual implementation. So here we see a widget class, which has some public interface with a constructor, destructor, and the method. And in its private parts, we forward declare type, but we don't define it, called impl. And after that, we have a pointer to it, which is in this case handled with a unique pointer. And in the implementation of this widget wrapper class, in the implementation source file, we're defining the impl type entirely. And after that, in the constructor of the widget class, we allocate a new impl in the destructor, we can actually default it here, because now we have the definition of the PIMPL class, and unique pointer can compile here. And the full method of the wrapper class just forwards the call to the implementation class. So what are the benefits of the PIMPL idiom? Well, it breaks the interface and implementation dependency. You don't have to drag the headers which are necessary for the implementation, and thus you get better compile times. And also, the wrapper type is always the same size. That means that we can actually ship an API which has a stable ABI. ABI is an application binary interface. And the idea is that if the ABI is stable for some shared object or some library, and it gets, no, how do I say this? So software doesn't have to be relinked together if the ABI stays the same. You can just relink and recompile one part of it, one component, and you don't have to relink the other one because the original has the same ABI and they can still talk to each other just like previously. And for example, the entire API of Autodesk Maya is done in this case, in this way. It uses the PIMPL idiom. But there's some problems with this as well. Well, it requires allocation. For each object, we actually allocate something which we assign to the pointer. But we can use allocators in some cases. Also, there's this extra indirection of calls because there's a wrapper type, but link time optimization that can probably help in that regard as well. And it's also more code to write. And there are many, many more gritty details about this idiom and implementation details. You can check them out, all of them, at that page. The next thing we can do is actually use virtual base classes. In this case, we have a base class and two factory functions. And we have in the implementation for these factory functions, we allocate a new type and we return it through the base class pointer. And these both derived types are, in this case, implemented in the source file, which implements the factory functions. So this, again, breaks the interface and implementation dependency. So you can actually have more data members inside of the implementation classes which inherit the base class. It, again, helps with preserving the ABI, but unlike in our previous case, if we add a new virtual function to the base class, that actually changes the virtual table in memory for the binary, and it's no longer ABI compatible. But there again are some problems. It requires allocation. There's also this extra indirection of calls because of the virtual calls. And it's more code to write. And users now have to work with pointers instead of a value, which can be wrapped inside of a smart pointer, but still. So the next thing we'll talk about are precompiled headers. The idea is that you define one header file which should be used for your entire project. And there you put the most commonly used header files like parts of the STL or maybe some third-party libraries which are really necessary in most of your sources. And maybe, just maybe, some of your project-specific headers. So after that, when we define this header, we precompile it once with our compiler. All compilers have some way to do that. And then we can actually use this precompiled header for all of our sources, so they don't have to compile again and again and again the sources from the source code from those headers. The idea is that we should put only what's used mainly in our projects here. And headers here shouldn't change often. And that's why we should be very careful when we put project-specific headers in there, because each time something gets touched, the precompiled header has to be recompiled, and then the whole project has to be recompiled. And it's also a good idea to regularly audit the precompiled header if it still makes sense that something is in there, or maybe something else should be added. And precompiled headers are easily discarded by many, many people because they're a hack. But actually, they're standard C++. I mean, you don't break the language in any way, and they're so easy to implement. And the gains you can get are like 2, 3, 4 times faster build times for your entire project, or maybe just 20%, 30, depends. But sometimes the gains can be huge. For example, if you have heavy header files, like boost heavy, and you have small source files, many modularized 50, 100 lines of code source files, which include the same boost headers, well, there it would make a lot of sense to actually include and use a precompiled header. So yeah, they're supported by most mainstream compilers. One drawback is that you cannot have two precompiled headers for a source file. So for a project, you can have only one precompiled header, which has to be included everywhere. But at least it can be conveniently force included through the build system with compiler-specific flags. So you don't have to always start your source files with include that precompiled header. And also, there's build system support. Some build systems support precompiled headers natively, like it's just some switch or a directive in the build system. In the case of CMake, there are some modules which are on GitHub, which can do the same. The next thing we'll talk about are Unity builds, also known as amalgamated or jumbo or single compilation units. The idea is that if we have a lot of source files, we can just include them in a single source file and compile that source file only once. So if the separate source files we're including here include the same headers, and those headers have include guards, so they're only once included, in that case, when we do this, we'll actually compile those headers just once, only from the first inclusion inside of the big Unity source file. And also, when we're doing this scheme, we don't have to have only a single Unity source file, because if we have 1,000 source files, we can split that in 10 Unity source files with 100 in them each, right? And what are the main benefits? So yeah, a header file will be parsed only once in this case. Also, there are less compiler invocations, because 100 compiler invocations compared to one is different. Also, the same templates aren't instantiated again, and again. For example, stud vector with integer, it doesn't have to be instantiated for core and widget CPPs, but only for the Unity file only once. This is again a highly underrated technique. It can give amazing benefits, like 4 or 5 times faster, 10 times faster build times, sometimes just twice as fast. But it's also a big misconception that this is because of reduced disk I/O. No, that's not the problem, because the first time a header file is included somewhere, it's cached by the file system. File systems are very, very aggressive in their caching because they're so slow in retrieving things, so it makes sense to be aggressive when they cache things. And also, when we do Unity builds, there's less work for the linker, because there are less weak symbols to remove and fewer object files to stitch together. Techniques like this are very used in game studios. For example, in Ubisoft and the Unreal Engine, they've been used for decades. And since recently, WebKit is trying it as well. So what are the pros? Well, you can have wildly faster compile times. And the best gains are, again, when you have short source files with heavy includes, like when you include boost geometry, for example. And also, it's the same as link time optimizations, actually, because you don't have separate source files, so separate object files, which you have to link time optimize interprocedurally, which is a separate flag for compilers. But you actually get those in cross-translation unit optimizations for free. And compared to link time optimizations, so link time optimizations, when you turn on those flags for your compilers, your compilation actually becomes 2, 3, 10 times slower, especially with old link time technologies. And so this is faster builds and link time optimizations. One more thing. This is the most reliable way to actually catch any one definition rule violations. There are many tools with the sanitizers or flags for GCC and Clang, but they're not very reliable. At least 2 years ago, nothing worked for the cases I cared about. And the only way to actually catch such ODR violations were to use a Unity build. So suppose somebody defines somewhere a structure with a method inside of it, and it's implicitly inline, so it's a weak symbol. And that piece of code can be in a header, but he put it in a source file. And someone else wants it in another source file. And instead of factoring it out in a header file, he just copy-pastes it. And then somebody needs to change something in the other source file in the implementation of the method. So now we have two different implementations, but they're the same weak symbol. So the linker just removes all of the weak symbols except for one, which are the same, and uses that for the binary. So what you will end up is thinking that you're returning 66.6, but actually you get 42 everywhere in your program. And this is about cases where you actually have successful compilation, but you have violated the one definition rule, and you actually have a bug in your program. So Unity builds can catch these most reliably. And also, they enforce code hygiene, because you need include guards in your headers for sure. There will be less copy-paste like what I showed here. And but there are some problems with this technique as well, because it might slow some workflows a little bit. For example, you want to iterate on a single source file quickly. Only that's where you'll be developing today. And in that case, it might make sense to actually remove it from the Unity source file. Proper Unity build configurations can support such a workflow when you actually say, I don't need this source file inside of the Unity source files, so I can compile it just like normally. And also, Unity builds can sometimes interfere with parallel compilation. And what do I mean? So suppose one of the Unity source files, if we have 10 of them or 8 of them for 8 cores, one of them ends up with the heaviest source files just by chance, and it can still compile for a lot of time. And in that case, we call that a long poll, because all the other parallel jobs, all the parallel compilations are done, except for one, and we have to wait for it as well. But in that case, we can just reorder which source files get paired with which source files, and we can fix that parallelization problem. And the other problem is that actually not all valid C++ continues to compile. So if you have anonymous symbols with the same names in different source files, or a static symbol with internal linkage, and when you include those two source files in a single Unity source file, they'll actually clash. So you have to rename some things, but at least you get a compile time error instead of it compiling. Also, sometimes you get overload ambiguities just because something is present which previously wasn't. And yeah, maybe using namespaces in source files will be a bit of a problem sometimes. And the preprocessor also can be a little bit of a pain. But the bigger issue is that sometimes you might get a miscompilation, which means that the project actually compiles successfully, but it's in the wrong way compiled, because some other overload got chosen, or the preprocessor did something because one source file was included before another one, and it wasn't intended, but it happened, but it still compiles. So the only reliable way of catching miscompilations is to have a good test suite. So this is actually, I've never heard of anyone complaining about this. This is just a theoretical issue. All the projects which use Unity builds have never complained about that. But it's possible. So I wouldn't advise, I would advise against shipping a production release of your software with a Unity build, because you might have missed some bug like that. So how do we maintain Unity builds? Well, for CMake, there's an optional module which does that. The fast build system supports them out of the box as well, and there's experimental support in Visual Studio. Also, all of these solutions, they can produce multiple Unity source files, except just for a single one, which is good. And you can also exclude specific files for when you want to iterate over them, or if they're problematic for compilation with other source files for some reason. And there are also other build systems which support build system, Unity builds out of the box. And also, there's a patch which might get merged inside of Clang, and the idea is that that patch aids in the Unity build support in the Clang compiler itself. So it changes the names in anonymous namespaces, for example, in different source files, without the programmer actually having to change those. So even if you have the same name with internal linkage in different source files, that could actually compile. So with this patch to Clang, they managed with very, very small amount of changes to the Chromium code base to actually build it with Unity builds, actually part of it. And they had a good speed up overall. but not that much actually. Oh, actually 3 times, so it's 30% of the original build time. So 3 times faster builds for Chrome, that's good. Many people want it. So, next thing. Inlining, it's good for runtime, especially if it's moderately done, but for compile times, inlining is actually bad. And if we don't care about that much performance, we can have an optional debug build where we explicitly disable inlining for some functions or entirely or something like that. Or perhaps, what do I want to say? If we have a construct which is very many times repeated, or like a destructor which is implicitly inserted every time we return from a function. So if we have a complex type with a big destructor which might get inlined, and we have 10 return exit points out of that function, and if that destructor gets inlined, we might have 10 times the destructor actually inside of our function. And that's implicitly, that we don't see that. We don't think about that usually. And you might be surprised what even runtime effects you might have by annotating destructors as not inline, to actually tell them you shouldn't be inlined ever. And for testing frameworks, I should know, it's very, very good to actually annotate your testing functions, which are the asserts you write, because you check many conditions, and each check is actually a function call. And if that function call gets inlined 100 times inside of a test case, that doesn't make sense in compile times. So those checks shouldn't be inlined, actually. And my framework does that, and actually gave a talk about it here last year, and you can check that presentation. So, special member functions, we shouldn't pay for what we don't use. So it might be a good idea to explicitly delete the special member functions we don't intend to use anyway, if they will be actually generated. And some libraries even actually default out of line such special member functions, so they're not in the header, so they're not implicitly in line, and so the linker doesn't have to resolve a bunch of weak symbols. But this I wouldn't do it, because the gains will be actually very, very tiny, in the milliseconds for a bunch of types. So, but it's something, it's a factor for some libraries. So, templates. Suppose we have this template, and again, this is a bad example, but it illustrates the point. Here, the size method, it just returns the size integer from the vector class, and it's not dependent on the template type. But when we instantiate this template many, many times, we'll actually have the size method instantiated many, many times. And that's unnecessary work for the compiler and for the linker if it tries to remove identical symbols. So what we can do is factor out such template argument independent code out in a base class, and then we inherit from it in our templates. So only the minimum amount of functions get instantiated for that particular type. And also now we can easily actually factor out the stat size function out of the header file entirely, because now it's not a template anymore. Again, if you're concerned about about inlining, link time optimizations or Unity builds. And also in the first case, when the size was part of the template, yeah, the linker can fault identical such functions, but that's an optimization, that's extra work, and it can only do that if you never take the address of them. The next thing is C++ 11's feature extern template. So here we have a header which defines on the left, right? It includes vector, and it also defines an identity template function. And somewhere where we are gonna use that header and that template function and vector, we can say extern template and the specific template instantiation. And that means that in that particular source file, in that translation unit, that template shouldn't be instantiated. It will be done somewhere else. And later when we use them, when we use a vector of integer and identity of int and float, it compiles successfully. But it will expect that somewhere else you have explicitly instantiated both vector for integer and identity for integer and a float. So yeah, this was brought in C++11 as a feature to aid in compile times and savings. And again, in this case, we'll still have to parse the template in the somewhere CPP, but at least we don't instantiate the template there. And for the parsing of the template, we'll actually can use precompiled headers to even further reduce our compile times. And some STL implementations do this trick for their stud basic string template instantiation for stud string, because stud string is actually a stud basic string of char. So when you use stud string, it would be a good idea to have it already externed implicitly everywhere you use it, but it should be somewhere else explicitly instantiated. So we can also move functions which are templated out of header files. And in this case, the identity function and the calculate method, they're just forward declared inside of the header on the left, but in where we implement them on the right, after their implementation, we explicitly instantiate them for all the uses we expect to see in the entire project. So now the user can just use those specific template instantiations, but the problem here is that if they try to use a template which hasn't been instantiated somewhere else, with a different type, I mean, they'll get a link time error. But in the case of extern template, they'll just have to instantiate it there. But here, the problem with this technique is that where you explicitly instantiate the templates, you have to list all the types, all the combinations which you intend to be used. So yeah, that's about this. It's not very much used, I think. So, last year, Odin gave a great talk here at Code Dive, and in it he talked about the rule of Shio, which is one of his former interns, and there he came up with scaling of, not scaling, but order of cost of operations for templates, and looking up a memoized type, meaning something already instantiated, that's almost free, and it makes sense. But the heaviest thing, like 50, 100 times slower than getting up a memoized type, is using Sphene. So I really, really recommend watching that talk to get a feel for a lot of template metaprogramming things and compile times. Some other notes about templates. Well, variadic templates, you should be a little bit careful with them. Recursive templates, well, they're bad, especially when they don't get memoized. And recursive template arguments are even worse when actually the template arguments grow and grow and grow, and they get nested with more recursion. Also, now that we have const per width, we can deal with, we can have a lot less Sphene. So we can still have conditional, compile time conditional compilation, but depending on the types and what we're instantiating, but we can circumvent that Sphene mechanism, finally. And there are some tools you can use to play around with templates. MetaShell is an interactive template metaprogramming shell, so you can see when you write that template, what's actually going on. There's also the template tool, which is again Clang-based. It helps with profiling time and memory consumption of template instantiations. And you can also debug instantiations with it, and there are again tools for it. And these tools are very invaluable for people who actually want to write the state-of-the-art template metaprogramming libraries like compile time algorithms and things like that. These tools, they use them. And there's some other good talks about templates. For example, in this talk I'm mentioning here by Eddie, there he was investigating why thrift compiled code, thrift generated code took so long to compile. And thrift is a serialization framework, something like that. And the idea is that he used, at the end, he changed the code gen to emit code with type tags instead of Sphene. So he used normal overload resolution instead of heavy template Sphene machinery. and their compile times became like 10 times faster to compile the thrift-generated code. And also, in his talk, he talks about the F-time report switch for compilers, which gives a breakdown of how much time was spent in the different phases of compilation for a particular source file. And also, he uses template. And Odin actually is going to give this talk, which I'm mentioning here, in 30 minutes down there, this time as a 2-hour session. And again, he goes very in-depth about template manner programming and how to actually make it much more faster for compilation. And it's a very good talk. So you have to choose between his first part of that talk or my second part of this talk. Choice is up to you. No judgment. Not really. So about templates, there are more resources you can check out. So this book is maybe the most recommended one, the complete guide. And also there are a few nice examples and articles here I've listed. And there's one little to-do note for me to actually incorporate examples from there into my slides to how to actually make faster or slower the compilation of templates. So sometimes compilation is weirdly slow for some particular source file. And there might be actually a bug in the optimizer or the code generator in the compiler itself. And bug is not in terms of wrong code emitted, but very slow edge case where it actually takes 100 times slower to compile. And for GCC and Clang, again, there's the F-time report switch, which tells you from all the number of different translation phases of C++ what takes how much. And for Visual Studio, there's the BT, which is again for the front end and the back end. There's a switch for the linker. And also this flag, which was actually present in Visual Studio for 15 years plus, but last year it got popularized by Aras, who is working on Unity, and he wrote a blog post about it, the best unknown MSVC flag. And it's very good flag because it tells you for a particular source file if you have any functions which are like an anomaly based on some heuristic. For example, this function takes 7 seconds to compile. That's weird. Here you go debug it. So yeah, that switch is good if you are wondering why a big source file is compiling so slow, which functions are actually the culprits. And sometimes our binaries get bloated. I mean, it's a big topic, especially around templates. So there's bloatface. It's a tool for elf and macho binaries by Google. There's also a Windows tool. There's some other Windows tool. Again, all of these slides will be available online. They're actually right now. So you can check all the links and the tools later. And for Unix, there's that tool as well. Okay, so this is the end of the first part of the talk. After that, I'll continue with build systems, parallel builds, linking, compilation caches, distributed builds, hardware, physical design, modules, and other goodies. If you have any questions on the first part of the talk, we have, I see, 4 minutes officially.
Any questions?
There's one.
One moment, please.
I want to ask just for the link of the slideshow again.
Okay. There is it on the top. Any other questions?
Sorry, I don't know if you mentioned it. Is there any tool to analyze object files for, repeated code instantiation, maybe?
I think, yeah, just now when I mentioned the tools to analyze binaries and bloat, you can actually analyze with them.
You can also analyze object files, so you can see like which template is instantiated in every compilation unit.
Aha, object files, not final binaries. Well,
no, yeah.
I would suppose some of them, or maybe all of them, work on object files. I'm not sure. I haven't used them.
Yeah, because it would be really cool, because include what you use is really difficult to set up, because it has to analyze source files. But if you analyze object files, it could be lot easier, maybe.
Well, I would be surprised if those tools, or at least some of them, don't work for object files as well.
Yeah, it should. Okay, thank you.
Okay. Any other questions? Okay, there's one more.
Could you share some your personal stories of which of these techniques give maybe the most interesting results or most gain of terms of speed?
Well, of course, I've always forward declared what I needed forward declare, at least what made sense. Precompiled headers, Unity builds. I haven't made use of the PIMPL idiom for compiled times, but to encapsulate implementation details. Also, explicitly saying this should never be inlined. That's the biggest reason for doctest, my testing framework, to be so fast to compile, because almost nothing is inlined actually when you actually write tests, and it's still the fastest in terms of runtime. So, inlining is it's a complex topic, and maybe Unity builds and precompiled headers are by far the biggest thing I've had the pleasure of implementing. So, I guess I'll see you in 30-40 minutes for the next part. Thank you very much.
Okay.